Good morning. So we are now on the ninth lecture of our course, Vehicle Dynamics, and learning basics of mechanical vibrations. I'm just going to start today's class with just reviewing quickly what we were doing in the last class, and then the lecture points of today, stating I am going to start this particular lecture. So in the last class, we were just learning about forced underdamped vibration for a harmonic excitation. So harmonic excitation force is varying force. So f of t is equal to f naught sine omega t or f naught cos omega t. So we took external harmonic excitation forces f naught cos omega t, where omega is external excitation frequency of the system. And then we were looking at essentially the response, which was called a steady state response of your vibratory system, which consists of mass, stiffness, and damper. And the condition is under damped condition. So you have your damping ratio less than 1, not equal to 0. So that state, if you are giving such a harmonic excitation, we looked at response, what is called the steady state response. And we were also able to get the expression for amplitude, phase angle, and we defined importantly what is called the magnification factor, which is ratio of displacement under dynamic condition to that of static condition. And we were ended the last lecture stating that in case zeta value is 0, that is going to be an undamped free vibration. When undamped free vibration is with the external harmonic excitation, what would be the response? That's what we looked at in the last class, and we stopped the class. So I'm going to continue from that point in today's lecture. So let me just share my Active Inspire board for today's class. So hope you are able to see this screen. And this is lecture number 9. And today's date is 23/08/2021. So what we were seeing in the last class, the response was given by xp of t. So p is the particular integral part or steady state solution to represent as x cos omega t minus 5. So in this, what is x is called an amplitude, and that is obtained by the expression f naught by under root of k minus m omega square whole square plus c omega whole square. And in this, phase angle phi would be given by tan inverse of c omega by k minus m omega square. And of course, this is for the system where we have a spring constant k and damper with the coefficient c with this mass m is attached. And this has been given from its static equilibrium position, harmonic excitation force f of t. So f of t here was f naught cos omega t, right? So this was the force given, and we have defined importantly what is called the magnification factor. That's defined as the ratio of amplitude under dynamic condition given by this expression by to that of delta st, the amplitude, the deflection under static condition. So before this mass is attached, they are free. When the mass is attached, that is displaced by the displacement called delta st. That's called zero frequency excitation, or it is called static deflection, and so on. Right? So this would be given by. So I'm going to write the end formula instead of writing in terms of explicit appearance of Kc mass. I'm going to write it in this form, which we have seen in the last class. That was 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. This radical goes for this. So this was our magnification factor, where we defined this omega by omega n is the frequency ratio. So the ratio of excitation frequency to the natural frequency of the system. And this MF for zeta value equal to 0, that refers to undamped forced vibration for f of t. So what was our expression? Magnification factor. In the zeta, when you substitute 0, I'm going to have 1 by under root of 1 minus omega by omega n whole square. So this is that expression. So this is what we have seen essentially in the last class. I just quickly show you that what we had in the last class. So this was that we also looked at that with the forcing vector and displacement vector, that is the response, and how they are varying with respect to the angular displacement and the vector representation of all these forces acting on the mass. What are those? Spring force kx, damping force c omega x, and inertia force m omega squared x. Of course, that closing side is what is that amplitude of excitation force f naught. And we were seeing this, and this small correction that I had to do it, that's why I was taking it. So please note that this is in the square. I forgot to put it. And here again, please note that this is in the square. Right, so that's why I just have taken this, and please correct in your notes. And essentially what we were seeing in the last class at the end, looking at the magnification factor for an undamped forced vibration system, and the response is x cos omega nt. And we were able to conclude from here the value of ratio omega by omega n less than 1 or greater than 1. So less than 1, you have your magnification factor starts from 1 and it goes to infinity. And then when it is greater than, it goes to infinity when r is equal to 1. When r is greater than 1, you see that it again comes back from infinity to 0 value. And when you say amplitude, this plot which is there down in the negative scale can be taken on the positive side, and you can combine that amplitude always with the phase angle. So that's what is the plot that we are going to today look at it. And the concluding remark here is when r is less than 1, look at here, the response, steady state response is in phase with the excitation harmonic function. So they are together goes. When r is greater than 1, then you see that the response leads, or there is a phase lag. There is a phase lag. So it is not in phase with the excitation frequency. It is out of phase. This is out of phase. This is in phase. So we call this as in phase. Excitation response is the force vibration response is in phase with the excitation function. Here it is out of phase. Out of phase. Out of phase, right? So this is what we just have concluded in the last class. Let's now get into today's class, and this is the summary of what we did in the last class. I'm going to look at and start the class looking at what would be the total response of the system. You mean to, do you understand what you mean by total response of the system? So here in this case, look at here in this case, you look at, you have damping here. So the damping, anytime you have your fundamental governing equation here, which is mx double dot plus cx dot plus kx is not equal to 0, it is equal to f of t, is what is our governing equation. So the solution of this second order ordinary non-homogeneous equation would always have a total response in two parts mathematically, that is x of t is equal to xc of t plus xp of t. So this xc of t is very interesting. That's called a transient response, and this is called a steady state response. So we were discussing everything with respect to steady state response in the class. And transient response, how is it going to look like? So that is nothing but whatever underdamped free vibration response that we have seen, that is similar is what is that, and that is the starting point for today's lecture. So look at this graph here. So this one has got both the responses. So here XH of t refer to transient response, and XP of t refers to steady state response. And you see this function is the function which is similar to that of excitation frequency, in phase with the excitation frequency, you could say. And here this transient response is decaying exponentially, and it is going to be 0 at one point, and then this disappears. So the total particular integral part or particular solution only would ever exist as long as there is an excitation force present in the system. And if you add these two, and that would be your total response, something that it goes like this. And since this transient response is a momentary or a smaller time period and that disappears, then you see that would only the steady state response. So our interest is beyond this point. We just looked at only the steady state response in last class, and this transient response would die out. So any system is designed such that this period is what is called settling time. Settling time. So the settling time should be smaller in a system so that you would immediately get what is that frequency that the system to vibrate or system to operate. So the shaft supposed to rotate at a constant speed, then there should be transient effect should be removed. So when I do my vehicle steering, so taken turn, I should not have any transient vibration response. I should get my vehicle to go steadily. I should not have my top view when I see my vehicle should not vibrate like that with respect to vertical axis. So that that effect would be taken care by the damping present in our suspension. That's the role of suspension. So this is all in vehicle dynamics perspective. We are going to look at in detail in vertical dynamics part. And this fundamental of force vibration is important for you. That's why we are learning in this first module. So I hope you have understood this. So the total response x of t can be written as xh of t. So xh of t would be in which form we have already learned. It is x amplitude times e raised to minus zeta omega n t cos omega d t minus phi. So this is your undamped free vibration response. You see that is analogous. We could have seen that. And then your particular integral or steady state solution as today that we have seen is x cos omega t minus phi. So in this, what is x? What is x? What is phi? And omega is excitation frequency. Here omega d is the undamped natural frequency, and omega n is undamped natural frequency. It's damped natural frequency. So there is a relationship between omega d and omega n. So omega d is given by omega n times under root of 1 minus zeta squared. So this is all that we have seen. So this is the total response of the governing equation mx double dot plus cx dot plus kx equals to f of t, which is equal to f naught cos omega t. So if we have, this is your governing equation of force vibration, your total response and the equation would be given like this. So this is to be always remembered. So now let's continue with looking at two important aspects, that is characterization of magnification factor and phase angle of force to response due to.
Sir, can you just show the graph once more?
Which graph? This
the
one.
previous graph. Yes, sir. Thank you.
Yeah. Taken
Thank
down.
you, sir. Yes, sir.
Yeah. And now see, we are going to look at from this point of what we have done in the last class. So we were doing it, the magnification factor as function of omega by omega n. I'm going to plot the same graph now, not for one specific case that we have seen in this. That was when this value here, when zeta is equal to 0, you get this, right? That's a condition. So forced undamped vibration, how do you represent? in this zeta value equal to 0. That is why you see there is no Cx dot present in this equation. So this is your response. So when I introduce Cx dot in this, how this plot is going to vary, I'm going to explain you together amplitude and phase and hand in hand, and that would be very clear to you and would appreciate me, right? So that's what I'm going to do now. So let's just take these axes. So I have here one, here, and I have so what am I going to do is I'm going to plot now these things. I'm going to take here omega by omega n in this axis, omega by omega n in this axis. I'm going to have on this my magnification factor. And in this, I'm going to have phase angle, right? So let's look at now some important marking on this. So this is 1, this is 0, and this is 2, 3, and so on. So you understand what you mean by 1. So 1 here refer to omega is equal to omega n. It is the resonance state. So excitation frequency, when it is matches with the natural frequency of the system, what is called a resonance state would occur. At that time, you would have amplitude is infinity in case of undamped system. In case of damped system, that would be controlled and will have a maximum amplitude. So that is this line. So let's take a dotted line, vertical line, this axis. That's important now. And similarly, I would have here as well. Right? And similarly, on y-axis, I'm going to have magnification factor value 1, 2, 3, and so on. So 1, 2, 3, and so on. So I will have here also, this is an important one. When magnification factor is 1, that means what? My dynamic amplitude during vibration is same as that of what is that I felt at the zero frequency excitation or degenerate system it is called. So when I attach the mass with the spring and damper, what is the displacement that is there is called static deflection. If that is same for a dynamic condition as well, when this forcing function there, then that is called the magnification factor 1. So if it is 2, what is happening? It is amplified. If it is 3, it is further amplified. It can go to infinity when r is equal to 1. That's what we should understand this magnification factor. So if it is less than 1, what is the meaning? That means there is some kind of isolation that was there. That's what is magnification factor can be in multiples greater than what is a static condition, or it can be less than also. That we will see. And similarly, let me put here as well. Yes. Right. So now, when zeta value is 0, you know that is an undamped condition, and I would have my function. Let me just to put those equation here down so that it's easy for you to look at it. So what is my magnification factor? So that's 1 by under root of 1 minus omega by omega n whole square. You have to be careful in this square plus 2 zeta omega by omega n whole square. And on this side, what is phi? It is tan inverse of 2 zeta omega by omega n divided by 1 minus omega by omega n whole square. Right? So the variation of this, what is that we are going to look at with this frequency ratio. So when omega value, when zeta value is 0, that's very special case. When zeta 0, that's become 1 by this, which is undamped forced vibration. And we have seen that this would start always from 1. So you put zeta here, 1. So this term. So when omega by omega n is 0, that means omega excitation frequency is 0. So what is the value? That's going to be 1. So the plot would start from here, and that it goes smooth curve like this to infinity, and then again from infinity it will come down, and that would go to 0. Like this asymptotically. So this is what is when zeta value is equal to 0. When zeta value is equal to 0. So now if I introduce damping, I get my magnification factor influenced by this damping ratio value. And what is that? You would see it interestingly. This infinity go to amplitude brought down to a finite value. So you would have a plot now changes to this way. I'll have this peak goes up, and this peak is slightly on this side. It's not exactly on this line. I will see why it's so. And then it will be again decreasing, and it won't touch this. I'm trying to plot it. My hand is this slipping. So it is like this. So say this is value now, zeta value 0.3. Now zeta value keep increasing, what would happen? You would have these values going, and the peak is coming down, and then it will be this one.
Excuse me, sir.
Yeah.
So the graph, but it won't be touching the dotted line, right?
Yeah. Which dotted line?
The vertical
No.
one.
In this case, it would be touching. That's another case. You follow me. I'll explain you when it is.
Okay, sir.
Yeah. So there are different cases. That is a specific case when it will be going here like that. At that time, it will start from 0. That's a kind of base excitation problem or a working principle of accelerometer and so on. Don't get confused. And this is your case first fundamental magnification factor, right? Yeah. And that is what is going to be something like this. It is coming. So it is wavy here appearing. It is one single wave, right? It is like that, smooth curve. And say now this is zeta value 0.4, and this is zeta value 0.5. And I have the peak correspondingly here, only one more peak possible. That would be brought down like this. And this is zeta value is equal to 0.707. And then greater than this value, and you see when zeta value is 1, it is going to be something like this. And zeta value is more than 1, it is going to be all like this. But all are approaching 0 asymptotically. So this is zeta value 1, this is zeta value 2, 3, and so on. Right. So this is how this variation would come, and what are the important take from here is that points what we discussed. So let's look at that one by one. What is that? We call it as a characterization of magnification factor. So it is clear. I just summarize this again, once again for your benefit. So for an undamped system, the blue color one graph is there. So magnification factor goes to infinity. So for this case, what's happening? The magnification factor would go to infinity. At that time, R value is equal to 1. R value is equal to 1 is what? Omega excitation frequency equal to omega n, right? And then any amount of damping, that's zeta value greater than, so this is all you see, zeta value greater than 1, greater than 0, any value, zeta value greater than 0, you see that the magnification factor reduces for forcing frequency. So amount of damping, zeta greater than 0, reduces the magnification factor for all values of excitation frequency. That's what you follow here. And for any specific value of R is equal to, that is omega by omega n, a higher value of damping reduces the value of magnification factor. So take any excitation value, any point value here, any value here, higher damping value reduces your peak. And the degenerate system, that's case of R is equal to 0, you see your magnification factor is 1. So this statement to say this value I have drawn here, that has to be corrected, right? So this graph would all should come from 1, right? All should come from 1, like this. That's for 4 as it is increasing. So all the time when excitation frequency is 0, that is 0 frequency excitation or degenerate system, you see your magnification factor is 1, right? That's what is evident from this equation as well. Then the reduction in magnification factor in the response of damping is very significant at resonance or near to resonance. So look at here, when omega is equal to omega by n, that's R is equal to 1, you see this peak is very close. So damping works significantly, but the amplitude also that also there here, right? So the reduction in amplitude is significant when R is equal to 1. Otherwise also it is there, but here you could see from infinity suddenly brought down to a finite value, then it is further decreases. So that is very significant. Then magnification factor would approach 0, correct? MF would approach 0 when omega is much greater than omega n. So when your excitation frequency, or we can say this R tending to infinity. R tending to infinity means excitation frequency is very much high. That is why you require a smooth road surface. When you have a smooth road surface like in highways, you see that the wavelength of the peaks in the road texture is very small in micro millimeters. In such cases, what would happen? The excitation frequency is very much high. When you have excitation frequency very much high, you would get this magnification factor all goes to 0. So the vibration isolation is absolutely nice in our system. That's what you would see, that the difference of riding your vehicle on a smooth highway asphalt road and that of rough road on the or a country road on a rural areas. So the difference could be seen. There, if you see wavelength is more, then the frequency is smaller, and then excitation would be felt more here. So what is preferred is your excitation frequency should be much more greater than the natural frequency of the system. So this is an application. See, this is very beautiful. This basics of mechanical vibration is very important. So this is the requirement for an automotive side. So the road should be such that the excitation frequencies are going to be huge, so that you will not have any problem of vibration, other issues. On the other hand, you look at power plants where turbines are running at very high speeds. So when turbines are to run at very high speed, the excitation frequency omega is going to be in some 20,000, 30,000 RPM, 40,000 RPM, and so on. That's your excitation frequency. So your natural frequency should be so small in your shaft, which is rotating or carrying all the turbine rotors and rotating, should be of very smaller natural frequency. In such cases, you would have again their flaw-free system. Of course, the rotation should cross that, and that is what is called a critical speed, and that would be quickly crossed. That damping present in the system would take care that the amplitude is very less in shaft when it is crossing, and then the operating speeds are so high speeds, so that won't be a problem at all for smooth generation of power. So this is all something that you understand from this graph and so on. So like in the last class, I said omega is nothing but the speed of any rotating element. So if you are knowing RPM, n is equal to n in RPM, right? N in RPM, rotational speed, you can get that in omega. So what is omega? 2 pi n by 60. 2 pi n by 60. So n is radians per revolution per minute. So divide by 60 revolution per second, multiply by 2 pi, you get radians per second. So this omega is what is an external excitation frequency of the rotating shafts. Right? So this is that characterization of your magnification function. So on the other hand, let's look at now what is that variation in your phase angle. So look at now phase angle when zeta is equal to 0, in this case tan inverse of 0, so you'll have phase angle 0. So phase angle 0 here till this value. Then when again you see it can be either this or it can be either here. So here I should not put this 1, 2, 3. I should have this axis as 90 degrees, 180 degrees. The phase can be either 90 or 180 degrees. So what is that you will have now is that resonance when R is equal to 1, that is this case, and zeta value is 0, I would have my sorry, my phase for this case would be changing it like this. So the blue one you can look at in this as well as in this corresponds to zeta value is equal to 0. When zeta value is 0, it is undamped forced vibration. And in such cases, you see when R value is less than 1, you have 0 phase angle, and R value greater than 1, you have 180 degree phase angle. So that reflect what? That reflect this understanding of in phase and out of phase response. Right, in phase and out of phase response. So now what would happen if zeta is introduced? When zeta is introduced, you see this graph now, phase angle would vary between 0 to 90 when zeta value is greater than. So we have two cases. Zeta value is less than 1, greater than 0. Zeta value is greater than 1. Here zeta value 0 we have plotted, and here also this graph ranges r less than 1, and here it is r greater than 1. Here it is r greater than 1, right? And here it is r equal to 1. This is r equal to 1 point. So now your phase angle would vary like this. So when I have zeta 0.3, I will have my phase variation goes something like this, and that would be till here 90 degrees it goes, and then it is going to be something, and asymptotically it is going to reach 180 degrees. So this is for zeta value 0.3. So what would happen for 0.4? 0.4 it would be like this, and this is for 0.4. So this is 0.3, 0.4, and like that I can keep increasing 0.5, 1, 2, and so on. This is how it would be varying. So how do you summarize? What are the key characteristic points that you have to understand as far as phase angle is concerned? Are this? So you can see for an undamped system, when zeta value is 0, magnification factor goes to infinity, that we have seen. And what would happen to the phase? The phase will be changing from 0 to 180 degrees here. Right? For an undamped system zeta 0, the phase angle is 0 in this range, and the phase angle is 180 degrees above this. This implies what? The excitation and response are in phase and out of phase, which I was explaining to you. And when zeta value is greater than 1, zeta value is greater than 0. So here zeta value is greater than 0. That is this case. If you take, you see that the phase angle is between 0 to 90 degree. So zeta value is greater than 0, and you have your phase angle between 0 to 90 for this range when it's less than 1, implying the response lags the excitation. The response lags the excitation. We will see that in the vectorial plot after this. And when zeta value is greater than 0 and r is greater than 1, that is beyond 1 value, implying that the response leads the excitation. That's the meaning. That's why this angle goes like that, right? And when r is 1, the phase angle is given by 90 degrees. When R is 1, the phase angle is given by 90 degrees, irrespective of zeta value. Any value of zeta, you see this all crosses this. When R is 1, the phase angle is 90 degrees, right? That's to be important point. When R equals 1, phase angle is 90 degrees. So what does that implies? It is R is equal to 1 referred to a resonant state. At resonant state, excitation and the response would be at 90 degrees. The phase difference is 90 degrees, right? The phase difference between excitation force, that is F naught, and the response would be at 90 degrees. So this all will be very clear when I plot the vector diagram. I'm going to plot the vector diagram, and that would further help you to remember these fundamentals. So let's look at the plot like this. Let me take a new sheet, and let's look at now that plot like this. I'm going to vector diagram means you'll have this vertical axis and horizontal line. So let's have now this point is O origin, and I have my excitation frequency, excitation force vector referred by this. So this is my F naught. And F naught to the reference, how much it is? It is by omega t. So this angle here is omega t, right? Then I can write f of t is equal to f naught cos omega t. That is projection on this. Now the response lags this excitation. So that would be this. This is my response, x. And that lags this by what angle? Phi angle. So what is this angle? So this angle is omega t minus phi. That is why you have your response xp of t as x cos omega t minus phi, right? So now, because of this displacement, what do you have is this force k times x. So this is my displacement, dynamic displacement, and I have my stiffness. So that would be k times x. So it is in line, and this is my kx vector. And I would have my c omega x vector comes like this. This is my c omega x, c omega x. And I would have my inertia vector comes like this. That is m omega squared x. All right. So I can also have in textbook, you would see, instead of putting it, see, the spring force is opposite to that of displacement in spring. So you can take this on this side from here. So this entire length can also be taken it like this. So I just to draw that with the dotted line. So this length O to this, that's kx, and that would be in this direction. And then c omega x would be in this direction. And then this vector would be in this direction. So you can also see like this diagram. It is analogous, right? So I just take this vectorial addition of this. Why do I take this here like this 90 degrees? Can anyone answer? Can anyone answer? I would be happy that if you answer here, you get a chance. Is because you know that the velocity leads the displacement by 90 degrees and acceleration vector leads displacement by 180 degrees. That's a phase difference between these vectors representing simple harmonic motion that we have seen. That is why these vectors are like this. So this is 90 degrees, this is 90 degrees. So you should remember this. So this is my vector plot for omega value, which is much less than omega n. Or you can say here, I go with the R value less than 1 and greater than 0. So this is the plot. So if I have to look at R value equals to 1, that is omega is equal to omega n, how my plot will be appearing, the same plot, right? So that's what I'm going to draw now. In this, the amplitude f naught is constant. That's not varying. So what is our forcing function? F of t is f naught cos omega t. So this f naught is constant amplitude force. So this vector length, I should retain it, and that is going to be now with the phi angle 90 degrees. That's what we have seen. In this case, you see, irrespective of damping, at resonance, you have phi angle 90 degrees. So what will happen in your vector diagram? This would be 90 degrees now. So I would have my f naught the same length. I'm trying to plot here. This is f naught, and my x would be here. X's should be of the same length I take, right? So this length. And I'm going to draw now with the X is going to increase. X is going to increase because at resonance state with the damping present, so that would be limited, and I would have maybe some value of X here, and this is going to be my Kx value. And my C omega X value will be increased. See, this vector lengths are different now. This is C omega X, and my inertia vector m omega square X is this. And now it's 90 degrees. So what does that you understand? This is the resonance state. At resonance state, you have the spring force balanced by inertia vector, whereas the excitation force would be equal to that of C omega X, right? C omega X. So similar here, I can also have it in this way, dotted line. You'll see that varies from textbook to textbook. It's all our convenient what we use it. So here it is Kx, and it is m omega squared x, and this is C omega x, right? And this is at resonance here. So now here it is interesting, and the question comes, what is that maximum amplitude? So at resonance you get what? Maximum amplitude. How do I get? What is its value? That I'm going to explain you. And beforehand, let me just to finish my other vector diagram. So this vector diagram particularly to draw for you this. So when it is that, you see this phi angle is between 90 degrees to 0 for this case. And here when I have omega value is much greater than omega n, that's going to be R value greater than 1. And phi value is going to be between 90 degrees to 180 degrees. So you would see my vector plot now of these forces would be changed like this. My response is with this only. So let me have my response here. This is my X. And maybe this amplitude is less, so this is kx now. Kx means it is full length, and then I have my c omega x, and what does the increased is this vector length is increased, so that would be somewhat this much here taken m omega square x, and you see my f naught vector is this. This is my f naught vector. So this f naught vector, this all are same length. So pardon for that, assume that these all of same length. Since this angle phi value is now taken as an obtuse angle greater than 90 degrees, and you see that what has happened, this is that vector diagram. So your vector diagram can be plotted in this fashion as well. This is kx, d omega x and m omega squared x. So you see, this is the case when you have phi angle is between 90 and 180 degrees. So when it is going to be 180 degrees, this line and this would be in line, right? And that time it is when it can be phi value is 180 degrees, it can be at a very high frequency. Or omega is 0, you get immediately the phase angle greater than this would be 180 degrees, constant. Or less than r is less than 1, then it is 0. So it is only in phase or out of phase for a case of undamped free vibration, undamped forced vibration. In damped forced vibration, the phase angle would vary like this, except in this particular case when phi is 90 degree irrespective of damping. And anything other than that, you have this state. You have R value is less than 1. You have phase angle varies from 0 to 90 degrees. R value greater than 1, it varies from 90 to 180 degrees. And when R is equal to 1, you have either 0 or 180 degrees. And 0 refer to in phase excitation, that is impressed excitation force function and the response in phase, and it is out of phase, only 2 cases. So this is how you would summarize and characterize the phase angle variation as function of frequency ratios. So hope I made it clear, and we're going to end in another 5 minutes of lecture looking at what is this maximum amplitude, how do you find out? And you would have this doubt when you look at this critically, why this peak is slightly offset, skewed to this. So it's not exactly equal to r is equal to 1. It is slightly skewed here. What is that? Why the peak comes here? So such kind of doubts would be answered at this point, and that would be the ending point for our lecture as well. So what am I going to do? I'm going to take this function, magnification function, magnification factor, that's 1 by the root of 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square. So this function, so this mf is now function of what? Omega by omega n. So if I differentiate this function with respect to omega by omega n and equate to 0, I would get its maximum value to get mf max, right? So I'm going to do that differentiation. So I'm going to do dmf by d omega by omega n. So that's going to be, see here, omega by omega n is there. So 1 by under radical. So 1 by root of x is there. We know that differentiation. I'm just going to write. If you have doubts, you can ask. So that's going to be minus 2 into 1 minus omega by omega n whole square plus 2 zeta omega by omega n whole square to the power 3 by 2. Whole square to the power 3 by 2. Just let me have it, that I'll not make any mistake. So this is numerator, and denominator chain rule I have to apply. So when I take this function now, that's going to be 2 times of this entire thing, 1 minus omega by omega n whole square into, again inside it's 2 omega by omega n minus sign 2 omega by omega n. And again this plus, so 4 zeta omega by omega n. I mean to say this 4, how does it come? It's 2 into 2 zeta omega by omega n because of the square into again 2 zeta. So this is what is the differentiation of this function with respect to this, and that's equal to 0. If I put, I would get the denominator goes on this side. So this can only be, numerator only can be 0 for this. So when I do that, let me inside multiply. So this is -2 and this is come +4, 4 omega by omega n. And if I multiply inside, that's going to be minus of minus plus minus 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 4 omega by omega n power 3, because the square and this is 1 here. And this is going to be 2 into 2 into 2, 8 zeta square. So this plus 8 zeta, zeta square omega by omega n, right? This is minus or plus?
Sir, in the second part of the numerator, is there 2 outside twice or only
Yeah,
once?
so this is going to be minus, right?
Sir, not that, sir. In the numerator part, right? You wrote +2 into 2 zeta
Yeah.
omega by omega n into 2 zeta again.
Yeah. This
Okay,
one you are
fine.
saying?
Sir, no, numerator, sir. Numerator, second part.
Numerator, this one. Yeah, 2 into
Yeah.
2 zeta omega by omega n.
Into 2
That 2
zeta
is
again.
here actually. That 2 is here.
Okay, fine.
Actually, I should not have this. I made a
Yes, sir.
mistake. So this 2 is common for this all, right?
Okay, sir.
Now it's clear.
Thank you, sir.
Thank you. Thank you. So now if I multiply this -2 inside, I get this way, right? So this expression is clear to you. Just sit down later. Again, we can work out and see. And this is equal to 0. So now in this common factor is 4 omega by omega, and I take out, and that can be 0. Rest cannot be 0. So that's going to be 1 minus omega by omega n whole square. And here it is 4 that is taken. So it is going to be 2 zeta square. That's equal to 0. So this is very nice expression now. And I take this on one side, so it's going to be omega by omega n square. On the other side, I have 1 minus 2 zeta square. And I needed what? Omega by omega n. And now I'm going to call this omega with subscript p, because I'm making to 0 for to get fm. Sorry, mf. It's mf. Magnification factor. MF max. For MF max, you make this, so this is going to be called peak frequency. That's called peak frequency, and that's equal to 1 under root of 1 minus 2 zeta square. So peak frequency, omega p. Peak frequency, omega p, would be omega n times under root of 1 minus 2 zeta square. So remember that omega d and damp natural frequency is omega n times 1 minus zeta square we had, and this frequency formula is this. So this all are the interview question. If you are clearly stating this, you are cracking your interviews, right? When you say this is your favorite subject. So omega p is equal to omega n into 1 minus 2 zeta square is what is the frequency of excitation value. At that time, you would have peak amplitude or the maximum amplitude in your vibratory system. And this omega p is slightly less than omega n. That's what you see. Because of zeta, when you substitute, it's less. That is the reason why your peak in this graph is not at omega by omega n equals to 1. And that is at this point. That's omega p, right? The peak comes here. So that's what is that you see. This is magnification factor. Okay, so this we have understood. Now, what is the peak value? I should substitute this back in the function, right? I leave it to you as a homework to do, and I'll write that now. So putting this, put in MF expression, I get maximum value of MF, right? So MF max, the peak value would be now equal to this. Just to highlight that. Yeah, that is going to be this 1 by 2 zeta into 1 minus zeta square. And if damping is 0, I should not say. If R is equal to 1, at R is equal to 1, if excitation frequency is not, see, this is what for excitation frequency omega is equal to omega p. When omega is equal to omega n, R is equal to 1, what is my peak MF I'll get? That's not maximum, that's equal to 1 by 2 zeta. That's going to be 1 by 2 zeta, right? How do you say that when R is equal to 1? You can see here, you can substitute in this function R is equal to 1. This is going to be 0. So I have this. So this is 1. So 1 by 2 zeta, right? So from this function, it's clear MF when R is equal to 1. That means excitation frequency same as that of resonance frequency. What is that you get? This function is 1 by 2 zeta only. Because this term is 0 and here this is 1 and it's 1 by 2 zeta. But actual peak is not this value. So 1 by 2 zeta is not a maximum value. That is skewed to the left of your R is equal to 1 line. So if that is so, you have this. So this is all to be understood and remembered. Any doubts at this point? So this completes the forced damped vibration due to harmonic excitation. So if this is you have understood, if you want to pursue further mechanical vibration as a full course, we can go for non-harmonic excitation, like an impulse function or a step function or a random excitation and so on. I'm not going to do that. That's not scope of our module 1. And this is quite sufficient that you are learning for your vertical dynamic study of your lateral vehicle dynamics course. So with that note, I stop at this point. And if you have any doubts, you can quickly ask. Otherwise, we will end the lecture and meet on Wednesday morning.